Pardon?
Should we see the speakers?
You want to see the speaker? Okay,
Yeah,
let's see the speaker. All right.
It's a little too minimal.
Yeah, but then we can move it a little bit. Yes,
Yeah, that's
perfect.
fine.
So we know that nobody else is like defensive PhD, you know, that somebody else is defending you. Okay, well, I think it's time. So it's a pleasure to have with us Aseel Farhat from Florida State University in Tallahassee, and she's going to tell us about intermittency in turbulence and the 3D Navier-Stokes regularity. Aseel, just we have a mixed audience here, some doing hardcore rigorous analysis and other doing computations and modeling. So take it easy on us. I mean, right?
All right, thank you, Idris, for the invitation, and thank you for the introduction. So today I'm gonna talk about like maybe 2 or 3 results and like that I have with Zoran Growich from UVA. And like these results are basically like more like a regularity criteria for Navier-Stokes based on intermittency or sparseness we see intervals. So, say that again. Can you hear me?
Yeah, we do. Somebody asked me to turn off the light.
So we're gonna consider the 3D Navier-Stokes equations in this talk, and we're gonna take it in the whole space. That's just to avoid any problems near boundaries, basically generation of vorticities near boundaries. And for this talk as well, I'm gonna set the forcing to be 0, but you can bring back the forcing and get all the results in a similar fashion. Also, we scale the viscosity to be 1, and again, this is something you can bring back into all the estimates and the assumptions we have in this talk. So what we know about Navier-Stokes, I think majority of the audience already like maybe familiar with this. So we have like most of what we have comes back or goes back to the early works of Dirac. We have what we call global in time, existence of weak solutions. And those weak solutions are basically the solutions in the finite kinetic energy class. So you start with initial data with finite energy, you remain finite energy with all the time, but you get like a bound on the gradient of the velocity, which is basically due to the dissipation in the system. Now, uniqueness remains open for these Dirac solutions. Like we have the work of Buckmaster and Bicol 2019. We have a non-uniqueness result in the class of finite energy, basically the class you be in L infinity L2 all the time. But other than this, like we don't have any other big or major results. The second result we have is concerned what we call the strong solutions. And those strong solutions are basically solutions starting with initial data in H1. So we have local in time, existence, and uniqueness. So you remain like in H1 for a short time, and you get more regularity like on the Laplacian, but you can't necessarily extend this time of existence beyond some short interval. To extend it, to get it to be global, you need some assumptions on the initial data, and you get like smallness type of a condition. So if you have small initial data in H1, then these solutions will be global in time. Now, these solutions are the class of classical or smooth solutions, these are the analytic solutions that really satisfy the problem in a classical fashion. Now, there are 2 questions remain open based on this, like for the weak solution, is it possible that these like form some type of singularities in finite time? And for the strong solutions, is it possible that they blow up in finite time? And these are kind of related questions, and this is basically like the 3D Navier-Stokes regularity problem. Now, to understand this issue better or understand what is the complication, we usually look at what we call the vorticity field, which is the curl of the velocity. And you see from the definition of it, it's the curl. So in a way, it kind of gives you some local measure of how much rotation you have in the fluid at each point. And if you look at this vorticity, and you look at the equation for the vorticity, so you simply take the curl, let's say, of the equation, then you get the equation for the vorticity, or the nonlinear term in the equation of the vorticity somehow breaks into two pieces. One piece, which is the transport piece, you have the vorticity transported by the velocity in the fluid. And then the second piece is this second like highlighted piece that what we call like the vorticity stretching term. Now, to close the system, whenever you have the vorticity due to the divergence-free condition, you can reverse the Laplacian, and then you solve back for the velocity. So these are the equations for the vorticity, and up till now, all our troubles in the analysis is from getting a priori bounds on the vorticity that they are global in time is basically this vorticity stretching term. So it is kind of understood, or by now, that this vorticity stretching term is the term in the equation, or what we call the bad term in the equation, that amplifies the vorticity in time. Now, why do we call it vorticity stretching term? There are many ways to explain this, but one, maybe rough cartoon to explain it. Let's say you have an element of the fluid with a vorticity, and somehow you expect, things to become a little bit chaotic in the system. So there is some separation of the top and the bottom of this element, and you expect this to happen very quickly. So as you stretch this fluid, you have conservation, let's say in compressible fluids, you have conservation of mass, which is basically conservation of volume. And for this, and on top of this, you have conservation of momentum. So you have to preserve the volume. So things has to be to shrink in size. The radius of this element has to shrink in size. And as it shrinks in size, conservation of momentum tells you that the vorticity has to amplify. So this is one way to think of why we call it the vorticity stretching. And it's the other way around too. If the vorticity is to become bigger and bigger in time, somehow the radius of these elements that they carry this vorticity has to shrink and shrink in radius. So this is kind of what we call the forward cascade. So you have the vorticity intensifying from going from from larger scales into smaller and smaller scales as it amplifies. So this is just to kind of give a meaning for why we call it vorticity stretching term. And again, this is a very rough cartoon. This is not necessarily what's exactly happening, but just to explain the idea. Now, so this kind of confirms that this is the bad term in the equation. Another confirmation comes from, if you look at the 2D Navier-Stokes, the vorticity and the gradient of the velocity are basically the vorticity will be a vector in the kth direction. The velocity will be in the xy direction. So this vorticity stretching term doesn't exist, or it's zero in the Navier-Stokes, in the 2D Navier-Stokes equations. And that's kind of another confirmation that says, okay, since we have regularity for 2D Navier-Stokes, this is maybe the problematic term in the equation. But then still we have to be a little bit more careful, because as you see, from the mechanism, even though the vorticity is intensifying, it just kind of concentrates on smaller and smaller scales. And we don't we should remember that these equations are dissipative. So we have a dissipation length scale for the equation. So hopefully things are moving towards a small and small scale that it is basically comparable to the dissipation length scale of the problem, and hopefully regularize the problem. So this term can be the bad term, but by the same time can be the helper in the equation, or can help us to lead us to maybe closer to regularity of these equations, if so. And this was a remark by Taylor in the 1930s, that you have to be careful, labeling this vorticity stretching term as the bad term in the equation. And this basically inspired so many computations. I think some of the earliest computations maybe come from the late 80s, but I'm gonna here I'm citing or showing the picture from Sheet, Jackson, Ortsak in 1991. So these are computations done for 3D Navier-Stokes and periodic box. And in this picture, the Reynolds number was only 77. Now, what is drawn in this picture, basically those are the vortex lines. And what do we mean by the vortex lines? These are the tangent lines, or the direction of the vorticity field. And the highlight, the regions in black, basically highlight the regions or the lines on the regions, or the vorticity direction in the regions of high vorticity in the fluid. Now the rest is just, you see this gray scale, which is the spaghetti shape. So these spaghetti shape, they don't have any geometric picture, or by eye you can't see any geometric shape for them. But the ones that are highlighted in black, which is the high vorticity, they come in shape of tubes. So, and those are actually what we call the vortex filaments. Now, one feature, just by looking into this picture, that you see that the direction, or basically like, yeah, the direction of those tubes, or those tubes are not twisting around much. They have maybe some discontinuities here and there, but on average, like it looks like the direction of the vorticity in these regions is somehow smooth. So this is one feature. You can capture it just by looking into this picture. Another feature is that these sets, or these black, thick black tubes, they don't cover the whole domain. They actually like come like they cover a subset, a small subset of the domain. And that's what we call like they are sparse or intermittent. They're not everywhere in the domain. So this actually like these two features that come from this picture, they initiated like some like works in the community, like starting with the pioneering work of Konstantin Pfefferman in the early 90s. And what was proved that if you, let's assume you have like a first blow up time, and near that blow up time or possible blow up time, the direction of the vorticity becomes Lipschitz, then actually this will prevent a blow up from happening, and you can extend the flow or extend the solution beyond that point. So like this condition on Lipschitz maybe is not very realistic, because again, there's some twisting, there's some discontinuities. So you don't expect them to remain like always like Lipschitz all the time. So this actually like initiated a bunch of works in the community where like the relaxation on this Lipschitz conditions, like the conditions from Lipschitz were like downgraded a little bit. Like just to mention the work of Grovich in 2009, which is this Lipschitz condition was dropped H1/2, but then there is some other like modifications or relaxations also by Grovich, where you can somehow allow the space to have some discontinuities in the domain, somehow to take into account points like this. And still, like if this happens near like the first possible blow up time, this actually stops the blow up from happening, and you can extend the solution beyond that point. So this is just to mention like the results related to the first feature, which is related to the direction. Now, the other feature that we will focus on today is the feature that these regions of high vorticity, they don't basically like cover the whole domain. They cover just a small subset of the domain, or a thin subset of the domain. And what you see here in this movie, or well, just like it is like a snapshot in time. So this is like you run like your simulations, like I take a snapshot in time, and then I'm just only rotating the box so you can see these red sets, which basically are the high or regions of high vorticity in the fluid, so you can see them from all angles. And you can see that they are really thin compared to the volume of the box. And like this is the level sets. So this is like when you take it equal. So not just only the super level sets, you take the level sets, and this is basically the structures like that you will see in the fluid. Now, this related to this, like maybe one of the earliest work related to this is the work of Giga Miyakawa in the late 80s. And what was proved at that time is that if you start with initial data, that it is like some measure valued, like initial data, which is small in this class of Moray, like some Moray class, then actually the solution will remain global. We can prove existence, uniqueness, global in time for the 3D like Navier-Stokes equations. And this is like a smallness result, which is somehow consistent with what we have in the literature. And I'm going to mention some kind of smallness results as I go in this topic. But this is kind of like you can count it as one of the first related to the fact that the regions of high vorticity, they cover a small or thin domain or thin subset of the domain. Now, I'm going to focus more on the work of Grovich in 2013. And this was like a regularity criteria based on this picture. And what Grovich did in 2013, he basically looked at, if you look at the super level sets or regions of high velocity in the fluid, and if those like near the first blow up, like possible blow up time, they become sparse enough, and I'm going to define what I mean by sparse enough in a second, then actually this prevents the blow up from happening. So this was the result of Grovich, and we lifted this work of Grovich in 2013 to the vorticity instead of the velocity in 2019 with the Bradshaw. So we took it from the velocity to the vorticity, and there are like maybe major reason why we were doing the vorticity rather than the velocity, because all the computations I've shown you so far are basically vorticity. So they're not really velocity. You have a similar picture for velocity, but for vorticity, things are more sparse. It's more anisotropic. So you expect that any condition you put on the vorticity or super level sets of the vorticity is more relaxed than any condition you put on the velocity. But lifting the work from velocity to vorticity adds some extra complications. There are some terms that you have to take care of maybe better, which is basically the vorticity stretching term. So you have to keep an eye on the vorticity stretching term, so to control it as you go into this analysis. Now, another reason to lift things from velocity and vorticity, which may become clear in a few slides, is you actually get more. Like there is something more you can say on super level sets of vorticity or you gain more information that you don't necessarily gain on the level of velocity. So I'm coming back to sparseness. So before I state the theorem, I have to explain what do we mean by sparseness, or by wording, it is basically that these sets are thin or small compared to the whole domain. So one way to define sparseness is by looking at the volume of those sets compared to the total volume. So this is one way. Another way is to relax it a little bit to make it local. So instead of looking at the volume of the set or these red sets in the whole domain compared to the whole volume, to the volume of the whole domain, you look locally. So around each point, you have a ball of radius r, and then you kind of measure the volume of the set in this ball compared to the volume of the ball. And you want this to be small. But you can even relax it a little bit further. And instead of taking the 3D measure, the volume, you can take the 1D measure. So locally in the domain, you just take any point in the domain, you draw a ball around a point, and somehow you want to measure, you find the 1D measure along one direction, going through this point of these super level sets or regions of high vorticity. You want to find this 1D measure compared to basically the length or basically the diameter of your ball, and you want this to be small. So it is local. So at each point you can draw the direction, and the direction can change from point to point. And it is this at this point it is local. And what we care most about is actually in all of this definition is the R, the scale R. Delta is manageable in all of our work, this constant delta, you can get any delta you wish, but the scale R is the most important in this definition. Now, the scale R, one way to think about it is that, the scale of sparseness in this definition somehow is related to the, to the radius of this structure. What is if you look at these tubes, how big is this radius, or what is the radius needed so that these tubes, this radius of these tubes, give you regularity or not. Now we're gonna apply, as I said, on super level sets, and there are so many ways to define regions of high vorticity. For this work, we took it basically super level sets compared to the L with respect to the L infinity naught. So at any snapshot S in time, we just measure the omega and L infinity at that time, and somehow you found the regions that basically have a fraction, a greater, let's say, for example, than half of this omega L infinity at that time. So this is how we're gonna apply it. One further relaxation that we did. Oh, go ahead.
I have a question. Can you go back? So the definition for the 1D sparsity, if there exists unit vector or for every unit vector?
One vector. So per each point, you need to find one vector, 1D.
So there's one direction which is kind of sparse, sort of.
Yeah, along that direction, things look sparse. Yeah, you
the other directions, it can be okay. It could be thick in the other directions, yeah?
It could be thick in other directions, exactly. Only one direction. So you kind of look around, you find the direction where you see less of those supersets, and then you apply the theorem.
So it is it's one dimensional direction in which you are really not thick. Okay, good.
Yeah.
So you're minimizing this over direction. Okay.
Yes. So that's what it is. So actually what of interest would be the complement of that direction, in which then you can show that this is not bad enough to cause irregularity.
In a way, yes.
Actually.
Yeah. So one direction is enough to stop, basically maybe blob, but the rest somehow yeah, they don't count. As far as one direction is good to go, then you are good to go. Yeah. And that direction is not fixed in the domain. It can change from point to point. So as you move in the fluid, you can change the direction. Are we good? Okay, I'm gonna move. So another so this is one relaxation, that it is 1D and changes from one direction and changes from point to point. Another relaxation is that if you have, let's say, a vorticity like a vector field, that it is like it's a sparse, or the super level sets of it are sparse. So automatically it is easy to see that the components are automatically sparse. But any condition you put on the sparseness on the components doesn't necessarily imply that the full vector is a sparse. So we kind of relax the conditions in the theorems to go from vectorial. Instead of using the vectorial norm here, we're going to apply it on one of the three components of the vorticity field. And at each point, you're going to apply it at any component of the three. So if one component at each point becomes 1D sparse, somehow the requirements of the theorem still hold. And you can do a little bit more and just take only the positive or the negative part of this one component you choose at each point. And just to convince you, this is based on the computations I showed you. So the green are the level sets, let's say at some cut of the vorticity. And this is the cut, the green is the cut with respect to the volumetric norm. But if you look at, let's say, for example, here, the first component of the vorticity, this is the blue and the red combined. And clearly, it is more sparse. So any condition you put on the first component alone is going to be more realistic or really relaxed than putting it on the whole green set, which is the vectorial. But furthermore, you can either put it in either red or blue. So it's even less. And you can see this from here, blue is way more blue or red is way more sparse than just green. So coming to the theorem, and somehow I kind of mentioned the theorem by wording, but let me reword it once again. There are so many components of the theorem, so let me start with explaining the major components. So if you start with a vorticity, let's say you have a vorticity solution in L infinity, and actually those are the analytic solutions, as I mentioned in a second. So you have a solution of in L infinity for the vorticity coming from some initial data in L infinity with some integrability, let's say, for example, L2. And T star is the first time of possible blow-up time for this solution. So before T star, you see, you're assuming that things will blow up. So eventually the norm, the L infinity norm, will start growing. And you expect that at any level for L infinity norm, you're going to cross that level and never come back, because otherwise this will contradict that you have a blow-up. So at that, this is what we will call by words the escape time. It's just the time that you leave this level and never come back to it in terms of L infinity. So if beyond this escape time, in some small neighborhood in this escape time, you have a snapshot S, and at that snapshot, these super level sets become sparse at a scale compared to this row, then actually this will prevent blow-up from happening at this time T star. And the way we proved it is that actually this sparseness condition at this scale, what it does, it's kind of eventually in time, very small window of time, it will decrease the L infinity norm. So every time the sparseness happens, this decreases the magnitude of your L infinity norm. And so this is the way you prevent or you contradict the fact that you have a blow up at T star. Now,
you just explain again to us what's your definition of escape time?
Escape time is, you see, it's the time, let's say, I'm gonna call, I think I have a formal definition somewhere, something like this. So you have a solution, you see, and you have a possible block time. A time T is called escape time if at any time beyond this part time that the L infinity norm is way bigger or bigger, strictly bigger than omega at that time. So beyond this point, your L infinity norm definitely is greater than the L infinity norm at that point. So it is the level. You cross this level for omega and L infinity and you never come back to it again. It will keep growing.
Okay. So to make sense of this issue, I mean, do you know that the norm near the blow up does not oscillate? Namely, I know that the lead soup goes to infinity.
Yeah.
But do you know is after a certain time it's bigger than some number? Does not go up and then come down and go up and come down and go up and come down?
Eventually,
Do you have
such eventually, as you go,
argument?
sorry, keep going.
No, that's I'm asking. Do you know? I mean, to make sense
Yeah,
that
you
this
can actually like
is
prove
not
it.
vacuous statement. Maybe there is a blow up, but there's no such a blow. There's no such escape time.
You can prove it by hand. It's actually like yeah, you can prove it by hand that this has to happen eventually near, if you are close to blow up, like, or close to
Such theory that the set of escape times is not everything.
it's not necessarily everything, no. But this escape time, like at least one of them should exist, or maybe a sequence of them should exist. So it's not everything. It's not for all time, you just leave and never come back. But at least a sequence of them, like at least one of them will exist. That you just go, like it may like oscillate, but if you are still oscillating, you are not really necessarily close to this blow up time T star. So T star can, because in a way, every time you go deep down, you can still extend this time, like this time of existence will push you away from T star. You can keep pushing the T star a little bit till like the existence time, the local existence time will remain shrinking, that you can't extend beyond T star. So one of those, one should exist. And actually you can prove that there is a sequence of them at least.
I see that. Okay, that's good. Thanks.
So this exists, like at least one exists, let's put it this way. So, and we don't need to put it, like the condition doesn't need to be put at that escape time. Like the reason why we needed to kind of refer to it, because in a way we need to contradict that this escape time exists. So we want to prove, or we want to use this sparseness condition to somehow show that at the moment sparseness happen, omega s, this actually will dip the L infinity norm to go beyond this escape time, or this omega at this time t, at the escape time t. So contradicting the fact that this escape time will exist. And that's the contradiction. So the way the proof goes is that we use this sparseness to really like mimic exactly the picture you just described, that things will start growing, sparseness will happen, it will take it down. And somehow every time it tries to kick in again, you can't cross the level twice, because at that point beyond escape, you can't cross any level twice. You escape it once, you can't come back again to it again. And that's the contradiction you get. So sparseness as a control, if you want to wish, or you want to reword it on the L infinity norm. But you need it to be sparse enough with the proper powers so that actually you can prove that it is strictly less than, or contradicted to be less than this level. So the measure, like the reason why I highlighted the rho, because it turns out by the end that this rho is the analyticity radius of this solution. So these solutions are analytic, and this is like via the work of or following the steps of the work of Kukavica and Growich, and later by Gobrovich, you can prove that these solutions, like they are analytic, and this is their radius of analyticity. So this is at time s, this is the radius of analyticity of the solution at time s. And this is suggesting that the dissipation length scale of the problem should be maybe comparable to the radius of analyticity as expected. Now, the other numbers here, like, okay, what is rho, what is delta, what is h? These are actually just constants. You just have to play with the constants carefully so that you can close the estimates. But these are the minor, like kind of details in the proof. The major one that sticks, no matter what delta and rho and lambda you choose, no, sorry, no, not rho, not delta, lambda, and h you choose, in a way, rho is the one that persists. And that's why we highlighted it, and the exponent is the most important part of all of this. You need this half here. You need it to be exactly the radius of analyticity. Now, this is just a geometric explanation for this, how you apply this. You see, like at the time, the snapshot that you want to apply the condition, the length of the yellow line is basically has a radius of, is the radius of analyticity, or twice the radius of analyticity. And then you just, around each point, you find a direction where basically the intersection between this line and blue or red is the minimum. And if it happens along one direction, is good per point. So this is exactly what the theorem is. So I'm not gonna go over the proof. Like there are so many components, I kept them here just in case somebody asks questions later. But the trick is to use like some like harmonic measure, specific harmonic measure, so that you can, you know, like override or have a better bound than the maximum principle and get, you know, dip or prove that the L infinity norm will actually like decay a bit, contradicting law to happen. Now, where does this stand with, like, how does this regularity criteria stand or compare to what we already have in the literature? Just to remind everyone, we have the unique scaling for Navier-Stokes. And based on this scaling, if you see that you take this U lambda, and let's say you take the L2 class, which is the energy class, and you just calculate U lambda and L2, you see that it is compared to U and L2 by like up to an exponent of lambda to the -1/2. Another example that preserves basically the norm is L3. So L3 preserves the norm for U and U lambda. And so L infinity has a positive power or power exactly 1 for the lambda. Now, any class that is similar to L3, so basically preserved under the scaling, is what we call the critical classes. And the ones like L2, which is all the a priori bounds we have are kind of similar to L2. These are the supercritical classes, and that's why we kind of refer to the Navier-Stokes problem is a supercritical, because all our bounds are in this level, but technically what we need are on this level, because somehow the L3 is one way to think about this equality is that it's a good control norm. This is a norm that controls in a way small scales, large scales in an equal fashion, so you can control everything. So if you have any a priori bound here, you can control all the scales and you can get regularity. And you know, the scaling gap, what we refer to the scaling gap is basically the gap between what we need and what we need and what we have. So to compare, like to look at the literature, so one example is the L3, or in general, the Lorentz class L3 infinity. Another example of critical spaces are BMO -1, BMB -1 infinity infinity. And we have regularity criteria, maybe the most like non-trivial or really like more complicated one to prove is this work by Escarosa, Sherigan, and Surak. And the regularity criteria says if you have a bound on the solution in L3 infinity, and this bound doesn't have to be necessarily small, any bound, then actually you can prove that the solution will remain regular for the Navier-Stokes problem. Now, for other classes, there have been other works by so many people like Tataro, like Shvitkoy and Sheskidov, Canoni, Planchon. You can take, like, you have regularity criteria, but basically you need smallness now. Smallness, condition in BMO -1 or B -1 infinity infinity. And also you can prove that the solution for Navier-Stokes will become, or it can be extended to be regular. Or can, like, these conditions will prevent a blow up if you want to think about it this way. But the only one with no smallness conditions is the Escarosa, Sherigan, and Surak. Now, to compare what we have with this, we like, as I said, the exponent or this radius of analyticity is the most important component in the theorem. And this exponent was a half for us for the radius of analyticity. And this basically inspired the definition of what we call Z alpha. So Z alpha classes are the classes where super level sets or sets of high, like in our case of vorticity, because F will be taken the vorticity, the high vorticity, they become sparse at a scale compared to 1 to the omega to the alpha at each time snapshot. So in our like language, our criteria sits in the class Z1/2. And to just a quick comparison, you can easily like prove all of what's written on these slides. These Z alpha classes are basically like a parent class for the Lorentz class LP infinity. And the relationship is if you take LP infinity, you can easily show that you are automatically in Z alpha with alpha being P/3. So just to put everything we have and we need on one table. So we have the energy class. This is where all our a priori bounds stand. You see it is U and L2, which is equivalent to omega and L1. And this is the work of Constantine in the 90s. So omega and L1, so this is P = 1. And according to this inclusion, like you are automatically in Z alpha where alpha is 1/3. So this is the energy class for these spaces. For the regularity class, U is in L3, but this is equivalent to say omega in L3 half. And in our spaces, if you do like alpha equal P over 3, this is alpha equal a half. So our regularity criteria is like scales the same way that as all of those critical spaces. In other words, this space is one of the critical spaces if you want to think about it this way. Now, in terms of a priori bounds, again, we still stand at the class or the energy, the energy conservation of energy, but within this framework, we were able to squeeze a little bit more. So we only like the energy is Z1/3, but we were able to put like an a priori bound that scales like Z2/5. And Z2/5 in terms of scaling scales like L6/5. And you see L6/5 is a little bit better than just like L1 for the vorticity. Now to talk a little bit how we get this bound. Now to get this bound, and let me just first like explain how this bound comes, or it's not a bound for all the time. This bound that becomes eventual in time. And the way it goes, you start with a solution that's an array solution starting with a finite energy, and you wait for the omega and L infinity to keep growing, like because we don't have control over it. It's natural to assume that it's growing to infinity. So you're gonna wait for omega to become bigger and bigger and bigger in L infinity till eventually this number, whatever this R star is, and we have exactly what this constant is. When this R star becomes less than 1, a number that's strictly less than 1, automatically the super level sets of the vorticity, they become sparse at the same level. So you don't expect the vorticity or the super level sets of vorticity or the vortex tubes to become thin immediately. You have to wait somehow till like the L infinity norm becomes really big, intensifies, and eventually like, okay, this R becomes less than 1, and then things will start shrinking, and the size of those filaments will be comparable to, at each time shot, is comparable to this R star. And you see the exponent 2/5, this is exactly the Z2/5 class. This is again why we define these Z alphas, because the exponent is the most important thing in all of the scaling in all of these on these results. Now to mention how we prove this a priori bound, again, the priori bound only relies on the conservation of energy. We didn't use anything else. And somehow the proof of this is a little bit basic, because it came from some basic lemma related to semi-mixing. So, semi-mixing or mixing is like one of the popular topics or one of the popular problems in fluids. And there is like a lemma like that somehow the smallness of any negative norm actually, if the solution or if the function becomes small somehow in the negative norm, then automatically you have semi-mixing. Now, semi-mixing is kind of like our 3D sparseness definition. It's a 3D sparseness. So if you have 3D sparseness, automatically you have 1D sparseness. So we use this lemma somehow as a black box. We only just took this lemma and just did it in 3D. And we proved that if, for any function, if the negative norm compared to the L infinity norm scales like R to the 5/2, then actually you get 3D sparseness of that function F. And this R 5/2, like this is exactly what gives the 2/5 in the priori bound. Now, as I mentioned, this is basic, like the proof of this is just basic definition of negative norms. And there is room, actually, like there is like a big room to modify this lemma, but at this point, we don't know yet how to do that, because in a way to really to modify any exponent here, you will automatically modify the scaling of the a priori bound. But nevertheless, even if you modify it, the question remains open, like how can we use this a priori bound in the regularity problem of Navier-Stokes? So far, we don't know, and it's not like a trivial or easy problem to do, but in a way, give you maybe hope that there is something better than what we know, like that one day we can use to get closer into this regularity class. But maybe not, and probably not, but this is just to kind of give maybe some hope that maybe there is something more we can do. Now, to double check this framework, we tested this framework on what we call the Kida vortex. Now, the Kida vortex are basically solutions for Navier-Stokes, can be Euler too, but in this case, Navier-Stokes, that they start from initial data that it's really highly symmetric. And all of these high symmetries will be inherited to the solution of Navier-Stokes. So these high symmetries are basically mirror symmetries in the flow and actually rotational symmetry. There are two types of symmetries, but there are a bunch of them. There are really like 6 total in them. And somehow it's really not easy to write the equations, like to embed all of these into the equations, but you can still do this in Fourier space, and you can, you can have computations on these type of flows. And this been like one major example to fish for singularities for Euler in the community since the 80s. Because it was like believed that all of these high symmetries may cause some blow up, or singularities to occur in Euler. So there was something like, if you go to the literature, there is some intense works on Kida, just try to monitor how big is that infinity norm, does it grow, what happens to it. But in a way, all the computations we have, in a way, they are still Navier-Stokes because there is some viscosity here and there in the code. So this is the Kida. Let me just run it again. So this is starting from initial data. You see the level sets become thick and big, but till eventually, till the L infinity norm becomes big enough, then somehow these sets become sparse, or the radius or the size of them becomes smaller and smaller. And you see all of these symmetries that you can see them from this picture. So these are the mirror symmetries that enforce on the initial condition when you simulate this. Now, to really measure the size or get an approximate measure on the size or the scale of the size of these structures, this is the game that was done or developed by some group in Copenhagen. So you just do these structures. So these structures are the Kida structures that I just showed you in the movie, and the people the game players, the game goes, okay, what is the smallest? They will just go through or go inside these structures, and we will measure what is the radius of the smallest ball you can fit inside these structures as the people play the game. And from the data, this is what we got. So here is on the right hand side, the vorticity L infinity, and you see it's growing. You get a peak of it, but then eventually it just starts to dip. And actually, I don't know why it's cut on the full screen. It looks cut, but you can see it. It's it dips down. So there is a maximum for the vorticity, but if you wait long enough in time, this will dip and will never come back to that level again. Now, in terms of scaling, we want to kind of measure what is the exponent. How does this the size of the ball that people play, the size of ball that the people put inside these structures compare to the radius of analyticity? So this D is the radius of analyticity, and you just find the exponent. And what the exponent you find is actually that these radiuses eventually in time, they are compared to this D to the power 6/5. And if you compare it to our definition of Z alpha, this is actually the Z 3/5 class. So let me just remind you, Z 1/3 is the energy class. Z 2/5 is the a priori band we have. Z 1/2 is the regularity class. And from the data, if you wait long enough or eventually in time, you actually dip to Z 3/5, which is a subset of Z 1/2. And in a way, this is a computational proof that Kida is not blowing up. Kida is regular, but up till now, we don't know yet how to prove or give an analytical proof for Kida. But this inspires us that we really have to go dig into our analysis, either improve the priori bound, which is to somehow do something related to the mixing lemma and encode all of these symmetries into the mixing lemma, or from the other end, also improve the bounds on the analytics. But this is just to confirm that, or to see that this framework can be informative in some scenarios. But it's still the question remains open. What do we have the scaling gap closing? Okay, probably not. And at this point, definitely not. But it's a closing if you go into higher and higher derivatives, eventually you can take this whole framework from vorticity to the second derivative, third derivative, kth derivative in general. And you see the scaling gap will get closer and closer or smaller as you go to the, with K being going to infinity. And if you compare the priori bound, like compare it to the radius of analyticity, then you see in the limit as K, so R being the radius of analyticity, as K goes to infinity, this a priori bound somehow eventually, like in the limit or asymptotically, will match with the radius of analyticity, and you can close the gap. But this is all asymptotic as we expect from Navier-Stokes. This is like, but nevertheless, you can just see that this is closing as K goes to infinity, and this is the work of Grauwich and Xu in 2020. So one like just final thing I want to mention, this actually like inspired us and made us think how we can do things better. Are there scenarios where actually we can close the gap in finite K? Is it possible to find scenarios where this limit here, like these exponents, will somehow match eventually for large enough K? And one way to do this, again, the mixing lemma, which is like hard. The other is the radius of analyticity. And to improve any bound on the radius of analyticity, one way or the other, you need like to make your dissipation stronger in the equation. So it is natural to look at the dissipative or the hyperdissipative Navier-Stokes. Now, hyperdissipative Navier-Stokes, it has a scaling which is very similar to Navier-Stokes, except you have these exponents that basically like capture or carry beta. And it's the same type of scaling. And you can just see like by looking at the scaling that the energy class or the energy becomes invariant, or the energy class becomes critical for the case beta is equal to 5/4. And this being been known for a while, and this goes back to the works of Lyons in maybe late 50s and the 60s, you can prove that for any beta greater or equal than 5/4, you have a global and time regular solution for Navier-Stokes. Now, we still stand at this 5/4. So the region between 1 and 5/4 remain basically like an open question. Can we do more? Up to now, we only have some reductions, like some of them are maybe logarithmic in type, like this is the work of Tao and Barbato and co-authors in 2014. You just move from this 5/4 by a little bit logarithmic correction. Or there is another way of reduction, like reducing this 5/4 is you keep it 5/4, but if you write things in the Fourier component, you don't need dissipation on all the components of the velocity. So for example, in the equation for U1, you keep U1, dissipation on U1 and U2, and so on and so on. So you only keep 2 at a time into the equations, but it's still like the exponent, or is it still 5/4? And this is like more recent work of Wu and Jiang, Wu and Zhu and Yang in 2019, but it's still, as I said, 5/4 is still like stays. So in between 1 and 5/4, aside of these reductions, we don't have necessarily anything different between the hyperdissipative Navier-Stokes and Navier-Stokes. So anything we know or we don't know about Navier-Stokes, we can inherit it into this region of beta between 1 up to 5/4. So if we repeat our like mechanism, or like our framework, everything will go the same as Navier-Stokes, and we confirm this. Like this is like was done partly in one work with the student of Grauwich with his student in 2021, and later in our paper that's coming in a few weeks. So you can do everything we've done before. You can carry everything that we have done before from Navier-Stokes into the hyperdissipative Navier-Stokes. But if you do things the way, like the direct way, you still, like you will not be able to close the gap. You'll do it in the asymptotic. Now, we still believe that, and this is the a priori bound, and the a priori bound in this case is the same, because the a priori bound only depends or only uses the fact that the energy is conserved, and that doesn't see the beta in it. But you still believe that there is maybe more, or hopefully there is something more between 1 and 5/4. And to take advantage of this, we needed some extra conditions like on the solution. And it's natural whenever you talk about Navier-Stokes solutions that you consider 3 cases. Like one of them is, okay, what if we have laminar flows? What if we have turbulent flows? And maybe the more difficult one is the homogeneous flows. So I'm gonna like mention a little like one remark or one result on the turbulent scenario. And if you have any questions about the other, I'm happy to answer later. So for the turbulent scenario, so if you have turbulence, we expect generation of high derivatives, or sorry, the derivatives will intensify in the fluid. So the high derivatives will have bigger magnitude than the low derivatives. But in a way, you don't expect that things will become too big. You expect that there is a range of scales where, or range of, this is the J, so the order of derivatives. So there is a range where you can control these low derivatives, dj, by the high derivatives, dk. Now, there is, when you do this control, this constant, this mjk constant, somehow the amplification constant, we don't want it to be okay, uncontrollable. To do everything in the proof and to use this property on the derivatives, to control the nonlinear term, you need these mjk's somehow, when you sum, with the Leibniz for rule and things, you need things to stay summable. So you need to add conditions on how big, or how this mjk's will need to, to behave. But nevertheless, if you have a regime like this or a scenario like this, then you can go back to the proof and really improve all the bounds or the scaling or these exponents that we have on the time of existence. Now, this is maybe hard to look at. Let me give you one example where this theorem is actually satisfied. One natural way to think about it is that your derivatives grow like a factorial. So the jth derivative will grow like a j factorial, the kth derivative will grow like the k factorial. And this is expected, or not expected, I'll say it doesn't contradict the fact, or it comes from the fact that the solution is analytic. So for this Lorentz series, or a Taylor series to remain summable, you don't expect a growth that's bigger than k factorial. So if you have you can find a range of L and K, so that the jth derivatives in between the L and K are all controlled by the kth derivative, and K need to be somehow big enough compared to the initial condition, and the L not very far away from K. So if this is happening, then yes, you can improve the exponent on the radius of analyticity. Now, when you improve the exponent of the radius of analyticity, let me say that this is only on the initial condition. And actually, in our paper, we prove that if this happens at one point, then for this time of existence, this turbulence scenario will be inherited to the solution. So if this happened initially, then automatically this will remain to happen for the solution in this window of existence, or of this window of analyticity. So we're going to apply this condition in the theorem that I'm going to show you last, which is my last slide. We're going to assume that, okay, we have the 3D dissipative or hyperdissipative Navier-Stokes with any exponent beta greater than 1, any beta. And you assume that you have first blow-up time t star. But then let's say before the blow-up time happens, and you look at this escape time, and at one of those escape times, at one time, you get this turbulent scenario happening at that one point. If this happens at that one point, then in the window of existence, this will remain to happen. Things will remain the derivatives will remain to act, let's say, for example, this way. And furthermore, the radius of analyticity, which is I have shown on the previous slide, will become with an exponent, a nicer exponent, which is 1 over 2 beta minus 1 k plus 1. And this kind of magic exponent, if you do some comparison between this and the a priori bound, you can match them. For any beta, you can find a big enough k so that these exponents will actually match, or even better, you can prove that the radius of analyticity itself will become bigger than what actually the a priori bound is going to happen at that snapshot. So there is, again, turbulence happen at one snapshot, or one snapshot beyond the escape time. Turbulence start happen. It will keep for a small window. And if you look at the radius of analyticity in that window, beyond that, it is going to be bigger than the a priori bound, at the level k for some big enough k, which means that the a priori bound, or the size of the superlevel sets, will become smaller than what the regularity criteria needs. Because the regularity criteria needs, okay, you need the size of those superlevel sets or the filaments to become like at least or comparable to the radius of analyticity. But with this kind of like scenario, turbulent scenario, you can find large enough K so that for some superlevel sets for high derivatives of the hyperdissipative Navier-Stokes, actually the size of those filaments will become way or thinner or smaller than what regularity is needed, and this basically regularizes the hyperdissipative Navier-Stokes and prevents blow-up from happening. Now, this is still conditional because the way we describe turbulence, we describe it, let's say, with this, what we call the ascending chain. So you have ascending chain that you can control everything by the higher derivative. And there are these like other conditions. These can be relaxed a little bit. Actually, these you have to be careful about them when you mesh things in this theorem. But nevertheless, we were not careful, actually. We didn't care about what this is. But nevertheless, it is still conditional in a way that in this scenario, you can say more about hyperdissipative Navier-Stokes, that you can say that it is okay. Eventually, we close the gap, which while in the Navier-Stokes equation, if you repeat the same proof, you will stay asymptotic. So the point from all of this, just to kind of like say that there is maybe more in the range between 1 and 5/4 that we can say about the hyperdissipative that we still don't have. So maybe one day with more like analysis tools or something that we can really prove the regularity for the hyperdissipative Navier-Stokes in some range for beta greater than 1. That's less than 5/4. So there are the other two cases, the laminar and the homogeneous, but I think this is, I'm going to leave for this for questions, but you can prove a similar kind of theorem for these scenarios and in a way say, okay, under some conditional like cases for the hyperdissipative, you get more information than you can for Navier-Stokes in the range between 1 and 5/4. So I'm going to stop here. I know that maybe I'm just 5 or 10 minutes late, so sorry. And I'm going to take questions.
Thank you very much. Right on time. So let's see if there are questions within people who are here in person. Is everybody online? If not, then I have a question, in some sense, maybe comment. I mean, this line of research is in some sense getting the geometry of the singular set in the same lines of the work of Nuremberg about the singular set, how bad it is, and so on and so forth. Here you're having something different. It's not just the positive measure, but you're looking at what's happening in some direction. If it's nice in one direction, but it's not thick, then you're okay. Now, the Nuremberg is in 4 dimensions, namely space and time.
Yes.
And here, in some sense, all your analysis is in some sense capitalizing on this concept of escape time, which means that you need to have like the time or first time of blow up, what you call, or the maximal interval of existence, if you want.
Yes.
Is there any chance that you can generalize or improve Nuremberg with your tools? Like, here, like time is not, it's not one of the dimensions.
Yeah, time is a snapshot.
But have 3D and you look for sparsity in one direction. Can one do something, or do you see any future for this to be pushed 4 dimension to see something stronger?
At the moment, like if we go back to our proofs, all what we can prove that, okay, starting with any solution of Navier-Stokes will eventually become sparse in time for all time. But the sparseness is not, it's not good as what the regularity needs. So we don't really, this is the only thing that we can say, okay, that starting with any strong solution of Navier-Stokes eventually will become sparse up to this level for all time, but we don't know how to do more with all time yet. So the short answer for you is no, we don't know how to include time, and make it 4th dimensional results, like the Caffarelli-Nuremberg result. Not yet. But we can prove a bound on the sparsity, but it's not very good bound. It's not better than the energy class.
the other comment or question could be more related in some sense because of the technique. I mean, it's beautiful, it's nice. I'm just basically trying to understand and suggest. One of my issues with your approach, if you go to the very beginning, you capitalize on the L infinity norm of the vorticity.
Oh yeah, like the simple, that's the way we take them.
This is a nice norm for Euler. Etc. But for Navier-Stokes, maybe this is not the natural. Of course, it is nice geometrically to see where the vorticity is concentrating in the infinity, but maybe one has to look for integrated norm of the vorticity, so you can do space and time or something like that. Did you think about it? Because, for example, Caffarelli-Cohen-Ehrenberg says the vorticity in L1 in time, L infinity in space, it's finite, then you have regularity. But so, the Rodisserin is not even about the vorticity, it's about the LP norm of the velocity, LQ in time, and so on and so forth. So did you...
No, we didn't think about the time, how to include the time. We didn't think, I see, like maybe what you're suggesting is that instead of looking at snapshots, maybe look at a window and just average in time or something like that. But we didn't think about that. We didn't think about how to include the time. Now, in terms of LP, like we can't do everything LP, but we just chose L infinity because we like L infinity, but everything can be done LP. Like it's not a problem to take it LP. For NEP.
LP for the vorticity or for the velocity?
You can do them both for velocity or vorticity. Because
but for velocity, it's natural, because this is Rodisserin. For the vorticity LP, this is not a natural norm in some sense in the context of Navier-Stokes. That's basically my point. So if you move there, can you improve the results? That's my point. This is my suggestion. I don't know. But still beautiful. Understand? It's amazingly beautiful that you're getting this geometric structure of the potential band set.
Yeah. Okay. That's a very good.
Okay. David Rachel has a question here.
So just following on your comment, but maybe she can answer too. But one thing that continually bothers me in this area is the fact that most of the work is fixed in space, that you're looking at a ball, you're looking at something around some point where something terrible might be happening. What happens if you back off momentarily and say, okay, in Euler fluid, we know that vorticity is frozen as the fluid. It's a material element moving along. Doesn't that tell you that if you're taking the limit of viscosity going to zero, of course you're not doing it here, but you're thinking about a large space, don't you want to be somehow exploiting the fact that, okay, viscosity is going to destroy that property, but you're still wanting to move with elements. You want to move in a Lagrangian sense. Is there any way you can use Lagrangian information as a point moving with the fluid and say, improve on anything doing that?
Actually, this is, we cannot, like, this was one of our goals and we tried to work on it. And no, we didn't know how to use the Lagrangian and how to move with time with the Lagrangian. No, that we didn't, but we are aware of it and we really tried. We don't know how to do that. Now, in terms of, it's not a frozen in space. You see, like, okay, just to remark on this, x0 is like any point in the space. We just move the point and move the direction and just check the condition. So we're not really focusing the condition on one point in the space. So this is a moving point, but yes, like how to move in time and how to use the Lagrangian, we don't know yet, but it was something that we kind of tried to play with a little bit last year and we didn't know how to proceed.
Okay, one more question in the audience, you see?
Yeah, so people have been using the exponents of structure functions to characterize the sort of Hausdorff dimension of the active sets at various scales, and directly to characterize the level of intermittency. I was wondering if something could be said about this based on the a priori bound of the sparsity of the.
Yeah, basically, like if you look at the beta model, yeah. So we actually, like, before this hyperdissipative, actually, this is what we were doing. We were trying to use our framework to get like some bound on the beta and the beta model description. So this is actually like one of our biggest motivations to do all of this. But then we got distracted with the hyperdissipative, and then now we're coming back to it. So this is like a problem in the work. We have some ideas, but I can't say anything confirmative yet. But it is one of the things we are aware of, and we would like to use this framework to really apply to find what range of what is beta in the beta model description of turbulence. Yes, so thank you for the remark. This is something that we want to do one day, and if anybody has any ideas, we would be happy to collaborate and just discuss this further.
The minute you talk about structural functions, you talk about averages in time.
Yes.
Which means you can't really go with this machinery of like escape
Yeah,
time.
with averages in time. And still, like at the first step, we're gonna do like somehow a measure at each snapshot. Yes, but the average in time is still needs a little bit way more work.
Well, not necessarily.
It will make sense in a snapshot.
Yeah, not necessarily. I mean, you can do this in space, and you can compute structural functions in space. And people do this in practical reasons, but in principle, you can do this, based on a temporal snapshot.
Yes.
That can be done.
Oh, you're talking about spatial, but then you have to turn on the
Anna has a question. Anna?
Anna has a question?
Yeah.
Yeah, I just raised my hand just because I do have a question when the conversation is over in the audience.
Oh, okay. So it's private conversation you wanted, Anna? I don't...
No, I just wasn't sure if what will happen. So I did want to ask a question to Aseel,
Okay.
So that's why I raised my hand.
We have a moderator here, Cindy, who's not doing his job. Go ahead, Anna. Go ahead.
Hi, Aseel. Very, very nice talk. Yeah, so I have and maybe this is a dumb question. I mean, maybe you already said this, but can you track the dependence on viscosity in all of this?
Yes.
Because, I mean, the point would be, okay, if you can, formally, what do you get if you send the viscosity to 0? I mean, do you just get what you get by scaling, or do you get something else?
No, actually, when you keep the viscosity in, this rho will go to 0. So as nu goes to 0, rho goes to 0.
So you get what you will get by scaling. You don't get anything more. Okay.
Okay. Yeah, power like a nu to the 1/2, I think, on the top.
Okay. Okay. All right.
Well,
okay. Thank you.
Aseel, not to rush. Suppose you start with initial data, which is analytic. You don't expect this to go to 0 as viscosity go to 0. I mean, then the blow-up time, the T star will be changing in the viscosity. And as you know, for Euler, you have short-time existence and uniqueness if initial data is analytic. And the question is, what happens? I mean, because we know in periodic boundary condition, Navier-Stokes solutions converge to Euler as long as Euler exists. So within the interval 0 T star of Euler with initial data analytic, the machinery should go through somehow and something happens. So maybe it's worth really looking into.
Okay.
But for initial data analytic,
yeah.
Otherwise, because here you're capitalizing that the viscosity is making rough initial data analytic. There you start analytic and the radius might become 0 in finite time. At T star, it becomes 0, but maybe not before. Anyway, it's worth really. Okay. Does Anna make sense what I'm saying?
Yeah, it makes perfect sense. Thanks, Idris. Yeah.
My God, I knew I could count on you.
Very nice talk, yes. Yeah.
Thank you.
Thank you, Aseel. Wonderful talk. Really, frankly, I mean, maybe I should say off the record, it's getting better and better with time. It's like wine.
Yeah, you get, I think it just, you get familiar with your own problems better, right? Yeah, you understand things better.
But not us, so that's good.
Yeah.
Very good. Thank you very much, Aseel. Have a good day.
Thank you so much for the invitation, and hopefully I'll see you all in person sometime next year. Bye.
Okay, thank you all.